This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast.
This is Robert Blumen. I'm at the Mongo SF conference in San Francisco. I am joined by Dwight Merriman. Dwight is the CEO and co-founder of 10gen, the industry sponsor of the open source Mongo database. Dwight, welcome to Software Engineering Radio.
Thank you.
Dwight, I will be talking with you about NoSQL and Mongo database. First, please tell the listeners a little bit about your background.
So my background's technical. I started out as a developer, was the co-founder at DoubleClick and CTO at DoubleClick, built the original technology there, and after DoubleClick, started some new companies, including 10gen, which I'm working on now, which is which originated and sponsors the MongoDB project.
You've given a presentation that's available on the internet called The Transition to a Non-Relational World. Why is the world moving in that direction?
The original catalyst for that is the desire for horizontal scalability. So scaling a traditional relational database horizontally is a very hard problem. Distributed joins are very hard to do if you don't make any assumptions about the schema. In addition, distributed transactions are expensive to do. So there is a need for data storage solutions, in my opinion, that scale horizontally easily. And if we leave out joins and complex transactions, we can do that. So these new non-relational solutions, that's their characteristic. Now that's why the space got started. That was the catalyst, was really desire for horizontal scalability. But in addition, I think there's an opportunity to innovate around things like data models now that we're doing something that isn't relational to get some other benefits, including ease of development.
Why have relational databases come to dominate the storage market over the last 20 years?
That's a good question. Relational is 40 years old as a theory, so it's got to be one of the most long-lived and successful technologies in history. I can't think of anything more so. And they worked really well. I think one of the key things was there is a significant benefit to decoupling the data storage concept and data model from the program and the code, right? So, and enterprises have many applications and use many programming languages, and those languages change over time. Every few years there's a new programming language. So we don't want our data to be too tightly coupled to the code. And I think in the early days of object databases, that was a bit of an issue. The nice thing with relational is, there are no relational programming languages, where you have relation as a data type, really. So it's nicely separated from the coding environment, which almost paradoxically turns out to be kind of useful because you're going to have so many different pieces of code in so many different languages, and the code's complicated. So if I have to know the code to know the data, that would be a problem. In addition, it's turned out that SQL was a really powerful thing, which let us have a nice interface between client and server of these applications and have some standardization around that. So that was great, and that was obviously built on top of relational concepts.
You said one of the key drivers of movement away from relational is the need to scale out. Discuss the scaling issues that you run into with a relational data store.
Well, most relational databases, like if you said, I want to have a 10-node database cluster that looks like one logical machine, you can't do it. I mean, there are some you can. In particular, there are a number of solutions in the data warehousing and business intelligence space which facilitate that. So in that space, I actually think it's okay. But that's a special problem where it just turns out that the problem is easier there. But on things that are more, let's say, online or OLTP oriented, it's very difficult to build clusters. And really two types of clusters. One, just clusters on the LAN, but two, then clusters that are in multiple data centers and things like that too. That's even worse. So, it's very hard to make joins, distributed joins, fast.
You've talked about scaling and scaling out. Is high availability of the web world another driving factor in the move away from relational stores?
I think it is. I think there are pretty good high availability solutions for traditional databases. I think people are pushing that a little further in this new non-relational space. So I think it's more of a driver around scale, and then as people are willing to make the conceptual leap around this because of the need to scale, then they're finding some other benefits. You know, the general trend in computer architectures are such that you're going to need to scale horizontally. For a long time, vertical scaling was very feasible, right? We could get a bigger box for Oracle, and that's great. But what's happening is now that CPU cores aren't getting faster, so you can't get a faster CPU core, but I can give you 1,000 cores really cheap. But that means I kind of need horizontal scaling then.
So with cloud-type services, there's more of an economic force driving people to want to deploy on clusters of low-powered nodes.
Yes, so cloud computing, there's a really direct synergy between it and some of these new technologies. Cloud computing, horizontal scaling is a key attribute of cloud computing and elasticity. And we don't really have that in traditional databases. So you're getting on something like Amazon EC2, you're really getting kind of commodity like hardware. So the way to build a big system is use lots of boxes, not one giant box. So there's definitely a fit there. And really the weak link in cloud computing right now is the data storage layer. I mean, some of these new solutions are all young, and the old solutions don't map well to cloud computing.
Is it fair to say that if you look at relational databases as a product class, they're all more or less doing the same thing, and they do it a little bit differently? But when you talk about NoSQL, you're talking about a bigger family of systems with more variability?
There's a lot more variability. I think there is some variability in the relational space, especially if you look at the reporting world, where there's been a lot of custom things done with databases. But it's far more homogeneous than this NoSQL space is. And a big reason for that is it's early with this space, right? So there's an analogy, I think, between what's happening right now in NoSQL to the early days of relational, when you had Ingress and Informix and Sybase and DB2 and Oracle. And not even everyone was using SQL as the query language. There was a bunch of relational databases that used other query languages, and then there was a bit of a shakeout, and then it turned out there was a few winners, and they all used SQL. And so we're in that same kind of early shakeout phase. It's probably some of the products in the NoSQL space don't even exist yet that will be popular in 10 years. And some of the ones there today will eventually kind of become Informix or something, I suppose. So, but I think the space as a whole, it's growing really fast, and it's really exciting.
In the relational world, there are definitely some excellent open source alternatives, but some of the very big players are pure commercial closed source, whereas in NoSQL, there is a domination of open source models and in-house databases like Amazon's DB that are provided to you as a service by a cloud provider. Do you see that persisting, or do you see large commercial entities coming to dominate the space?
Yeah, it's very interesting. When I look at the most popular database segments, I really see what I think will be the most popular segments in, say, 5 years. I see three things. I see your traditional online OLTP style relational database. That'll still be there. That'll still be totally applicable for a set of use cases. It just won't be all use cases, which it used to be. There's also a segment which is really around data analytics, offline reporting, data warehousing, business intelligence. That's a segment too that exists, which is distinct, and which I think will stay pretty relational. But a different set of technologies from companies like Astrodata and Greenplum and Vertica. Then the third space I think we're going to see massive use of 5 years from now will be NoSQL, which will really be these non-relational or post-relational data stores that are horizontally scalable and that are suitable mainly for online data operations.
Within the non-relational space, you've talked about classifying the systems along several different axes. One of those axes is provided by the Cap Theorem. I'd like to delve a little bit into the Cap Theorem so we can understand it and then use it to talk about different types of data stores. In brief, what is the Cap Theorem showing?
So the Cap Theorem is a conjecture from Eric Brewer that was then proven and then became a theorem, which basically says in a distributed system, if you look at three properties, which are consistency, availability, and tolerance to network partitions, so that's the C and the A and the P, you can't have all three at the same time. And there's a proof of this. And so another way to say that basically, so we're talking about distributed systems here, so there's a network involved, right? So when the network partitions, part of the network is down. So what this really says is if the network is broken, your database is not going to work. This is not surprising if it's a distributed database. However, we do get to pick what doesn't work means. We can choose either it's down or unavailable in that situation, or we can choose that it's up, but the results are not strongly consistent, right? We have a weaker consistency model, not zero consistency, but some other weaker model like eventual consistency.
You've shown a triangle with the sides C, A, and P. You can think of each pair of properties as one corner of the triangle. So I'd like to look at those three corners briefly. So what does a CA data store look like? How does it behave?
Yeah, so basically a CA data store gives you consistency and availability. And then the question is then what happens if the network partitions? So if you get both of those, since we can't have all three, that probably means you get incorrect operation. So an example of a CA system would be a single computer, right? So if we run Oracle on one server, we think of it as having C and A, at least for, say, a client program running on that computer. But if you imagine, say, the memory bus is losing data, like you do a memory operation and it fails, that would be kind of like a network partition, and then you would get basically incorrect results. So that's kind of what a CA solution is. So in a way, CA doesn't even make sense because we're fundamentally here talking about distributed systems. That's the context of the Cap Theorem. So I don't think there really is such a thing as CA systems. So we're really picking between consistency or availability, and there may be a little bit of a dial between them. So we really are picking either CP or AP. And so, sometimes people will say Cap Theorem, there's three sides, pick any two. But I think that's actually wrong. It's either, pick C or pick A because you got to have P. You got to be able to tolerate a network partition and not corrupt your data, basically.
Talk a little bit then between those two choices about the C-type system.
Right. So C-type systems are strongly consistent systems. So if in the proof of the Cap Theorem, it talks about ability to do atomic operations on data entities. So really, where you can do something like, say, increment a value atomically, or do if balance greater than 10, balance equals balance minus 10 atomically, those type of things, where if you had two operations happening at the same time and you don't handle the serialization of those, you then could get an incorrect result of, like, say, negative 10 or something like that. So it's about, there's two things that come with the C of consistency, that with strong consistency. It's mainly about consistency of the order of application of operations and atomicity of those applications. But it's also about the data being fresh and immediately consistent. So that when you don't have strong consistency, you typically lose two things. One is you lose ability to do atomic operations, and the other is that you can read old data, right? So you can read temporarily stale data.
Can you give an example of, or some examples of systems or products out there that would fall into that C class?
Well, most traditional databases are in the C class, right? They support transactions and give you, if somebody committed an operation and you then do a read, you will guarantee to see the effects of that operation.
Among the NoSQL databases, are there some systems that are organized around that C-class principle?
So it's interesting because I think each of the products has an architectural sweet spot or bias, but to some degree, consistency is tunable. So for example, if we take MySQL, right? If you use MySQL on a single server, it's strongly consistent. But if I do master-slave asynchronous replication with it, and I do reads from the slave, that's eventually consistent behavior. So it really depends how you set the products up. But there are different styles of products. There are some which are strongly in the eventually consistent camp. There are some that are strongly biased towards the strong consistency camp, and there are some which are more in the middle.
So what does the A-class data store look like?
So really, the A-class data store is trying to maximize availability, and what that probably means is it's then, at least when it's configured as such, an eventually consistent system.
So we're going to come back to that term eventually consistent that you've used a couple of times. Could you give an example of a problem that you've seen where you would either choose an A-class or a C-class?
Yeah, so let's start with A-class. So systems which are basically maximize availability and are eventually consistent. So the interesting thing is people talk about Cap a lot, but there are a couple of reasons to use these eventually consistent systems. One is it does theoretically give you higher availability in the face of network partitions. But a lot of network partitions are what I call trivial network partitions, right? So if an entire data center goes dark and you have 3 data centers, well, that's a trivial partition. You could fail over to one of your other data centers and run from there because all the clients in the one data center are down, right? It's really the non-trivial partition is where the entire internet, the west coast of the U.S. can talk to the west coast of the U.S. and the east coast can talk to the east coast, but they can't talk to each other, right? That's a non-trivial partition and would be harder. And then if you had eventual consistency in an A-class system, you would be happy. But if you lose a whole data center and you have multiple data centers, you can handle it in either model generally. So a lot of partitions are trivial. Losing a whole rack, typically a trivial network partition. Now that said, so I think the availability aspect of eventual consistent A-class systems is a little overweighted. However, there is a pretty big benefit, which is the ability to have low latency reads and writes in the multi-data center configuration. It gives you that, right? Because you don't have to wait for the data to cross to other data centers necessarily up front. So latency is actually a key aspect of the equation that Cap doesn't capture at all, right? So we really, I think it's consistency, availability, and latency. I'm starting to think are some of the key variables.
Be fair to say then, what the NoSQL movement is saying is we have this whole space of design choices, and we need to use the whole space based on the problem and not just default to a relational database that may not take advantage of the problem that you're trying to solve.
Yeah, the way I think of it is just that, as Michael Stonebreaker has said, that one size fits all is over. We're going to see some specialization in databases now, right? We're not just going to use one tool for everything. It's not, we're not going to use MongoDB for everything. But there's going to be the right tool for the right problem, and depending on what you're doing, that tool will vary.
What sort of choices did you make with MongoDB navigating the Cap theorem?
MongoDB is more in the C class, so its sort of default configuration is strongly consistent. Now, the way I define NoSQL is I think all the solutions there do not do joins and do not do complex transactions, because if you leave those two things out, horizontal scalability is then very feasible. So we don't do those two things. But what we're really trying to do is beyond that, keep as many characteristics of a traditional database as we can. So we're going to leave out what we have to get horizontal scalability, but keep everything else. So in some ways, it's very traditional. We have secondary indexes. We support ad hoc queries. We support sorting. So there's a lot of those things that you expect in a database are still there, and which may not be surprising. But then if you look at some of the other products, it's a very different approach to the problem. So our approach is more in the strong consistency camp. So you can do atomic operations in MongoDB. So we let you do them on single data objects, right? So we do not give you complex transactional semantics, but we give you simple transactional semantics. We can do that and still scale horizontally, but having simple atomicity actually lets you do a lot of use cases. Obviously, there's some where you would need more than that, but then there's some where you don't need any atomicity at all. But there's a bunch which that middle ground solves, and we want to be able to capture.
What are people doing with MongoDB?
They're doing a lot. I think the biggest use case in the whole NoSQL space is just building web infrastructure and using these products as operational data stored web infrastructure, storing content of website, user session info, user profile info, logins, real-time performance counters, logging data storage. Those are all common uses of these systems, storing images, videos. But most online problems with data storage that are not highly transactional, they're a really good fit for. I think they're not as oriented towards reporting. You can do reporting with these systems, but it's just a question of, is it actually the best tool for that problem? And sometimes it's not. I think there's some very good reporting solutions in the relational in SQL space. So that we've seen a lot there, but also just any problem where you need massive scale or speed, people like it for. Also, people like these things for problems where they want fast development. So, for example, with MongoDB, it's a JSON database. It basically has dynamic schemas. So you can put JSON objects in the collection, and if you want to add a new field to one of these objects that's not in the other objects, that's okay. You don't have to run an alter table style command. So schema migration work is vastly reduced, and that fits really well with agile development. If you're doing a release a day, you don't want to do a database migration script a day. So that's a really good fit.
Are you seeing a lot more within a single web application or a single business that people are mixing and matching multiple data storage solutions based on the needs of a particular service?
Yes. So I think large organizations will use several products. So if I am a Fortune 1000 company, I would want, if I were CIO there, I would definitely want something like Oracle for certain things, for certain OLTP problems that are highly transactional. I would use a NoSQL solution like MongoDB for a lot of problems where I need fast real-time reads and writes of an online data storage, more schema and data flexibility, and really high speed and scale, and to make development easy. And then I would also get something like Astrodata or Greenplum or Vertica and use that for my data warehouse and BI work. Now that said, if I'm a small organization, though, I may not use all that thing. So we have a lot of users today who are building websites, and 100% of their data is stored in Mongo, and that's the only thing they're using. And that even includes their images, their videos. They're not even putting anything in the file system. So it's just kind of interesting. But I think as companies get bigger, you'll use a broader range of solutions just because you have the scale that it makes sense to get a little more specialized.
We've talked a little bit about the weakening of consistency. You have some very interesting articles on your blog about a range of consistency models. Everyone should go to the MongoDB blog and read the series of 6 blog posts about consistency, and you can see the diagram there. I'd like to go through these, starting at the most consistent and work up, give a brief description of each one. There's multi-entity transactions. I think I know what that is.
Yeah, so that's strong consistency with full transactions. So, debit A and credit B, and do it atomically as a transaction. So that's your classic database transactions you do with things like Oracle or with MySQL with NoDB.
And you have the strong consistency on a single entity.
Right. So this is what you can do with MongoDB. So we'll let you do, if you could debit A and credit B in MongoDB, if and only if they're in the same object. So if those are both in the same JSON object, you can do that atomically. But if they were in different data objects, that would be multi-entity, and you couldn't do that. So you can do atomic operations on single objects in MongoDB.
Immediate consistency.
That is where basically if someone's done a write, I'm guaranteed to see the results of that write immediately, is what we mean by that. However, that is different from having atomicity, because I could have immediate consistency but not atomicity.
Read your own writes.
Read your own writes consistency. So what that means is this is a looser form of consistency, which is saying that it may take a while for a write to be viewable by everyone, but it's saying that if you did the write, you're guaranteed that you will see it. And that's very useful. That's a very useful semantic to have in an eventually consistent system to help write correct programs.
So if you're the client and you've written something, you don't have to think about waiting around for your own write to be eventually consistent.
Right. So a good example is, if I, let's say I go on to my social networking site and I change my profile picture, right? And, well, if it takes a few seconds for that to show up for other users who view my profile, that's fine. But if then when I hit OK and submit that, I go back to my home page and I see my old picture, I will be very confused. So read my own write. It will avoid the confusion. It's okay if other people see the old picture because they didn't know the update happened, and it will not create confusion for them in this particular case. Now, but the interesting thing to remember there on read your own writes is sort of what's the scope, who is the you who's reading their own writes. It was the user of the website. So it's not just a single HTTP request to an app server. It was actually the next request, but it was for the same user where we wanted to read our own write. And so that can actually be kind of hard to implement sometimes because the load balancer may send the next request to a different machine.
Does MongoDB provide that level of consistency?
If you have strong consistency, you will automatically have read your own write consistency, and you'll automatically have immediate consistency. So there's sort of a hierarchy here a little bit, and there's actually a couple edge cases where you might have one thing or not the other.
Monotonic read consistency.
So monotonic read consistency is an eventual consistent system which has the additional property that for a given reader, if they've seen a read, they will then never see an older copy of that data item. So with pure eventual consistency, it's possible that, let's say that we have some data entity X, right? And let's say somebody writes 1 to it, and then 1 second later they write 2, 1 second later they write 3, 1 second later they write 4. If you have pure eventual consistency, you might read that as a 3, read it as a 1, read it as a 2, read it as a 2, and then read it as a 4. And then maybe read it as a 4 forever because you hit the consistency eventually. So I got values in a strange order, right? Which could be semantically confusing depending on what was happening. So with monotonic read consistency, if those writes had happened in that sequence 1, 2, 3, 4 over time to X, I may not see the most up-to-date copy instantly. I may not see the 4. But if I see the 2, I'll never see anything earlier than the 2 again. That's what monotonic read consistency means. So that actually intuitively makes a lot more sense to the programmer than just pure eventually consistency. One way to think about it is if you had, let's say we're using MySQL, and you set up master-slave replication, and you had 10 slave machines doing asynchronous replication from the master. And so if you read from the slaves, it's eventually consistent. And maybe as a client, you just read from a random slave because you're just trying to distribute the load. But each slave could be at a different point in applying the logs asynchronously from the master. So you could get results that are not monotonically read consistent in that configuration.
What I would take away from this as an architect then is I need to think about how much consistency do I need for an application. Every increase in consistency, I pay for it by making failure scenarios a little bit more difficult or increasing the possibility of downtime in certain failure cases.
Right. When you have higher consistency, you theoretically lose a little bit of availability, and you also lose latency in multi-data center configurations. What you gain is clear and intuitive semantics for the database. So that's really the trade-off. So I think with eventual consistency, you can solve many problems with it, but the semantics are surprising. So the developer needs to really think about, what do I need? Is eventual consistency sufficient? Or maybe eventual consistency with monotonic reads, I can solve the problem. Or maybe if I have read your own writes, like for the picture example, that would be fine. Or maybe I need more than that. Maybe I need immediate consistency, or maybe I need atomicity, or maybe I need full transactions. So the stronger the consistency is, the lazier we can be as programmers. You have to work harder the looser you make it. And I think all these modes are useful. I like strong consistency as a default, though, because it has the least surprising semantics. We should really be prepared to put on our thinking caps and say, hey, let me make sure I'm getting this right when we move to the looser consistency models.
So when you say the programmer has to work harder, what do you mean by that?
Well, there's actually a couple ways. One is you just got to be careful that your design is correct. So, for example, if you just say, okay, I'm going to use an eventual consistency. Let's say I'm going to use Amazon SimpleDB in eventual consistency mode. It actually has tunable consistency now, but let's say you use the defaults. And, you let someone update their profile picture. Well, then they go back to their home page and they see their old profile photo. They're confused. Well, having the user confused is bad. That, in a way, could be a design bug. But so did the programmer think about that, or did they just kind of assume it would be fine? Now, that's an example where there's a little bit of pain because it was eventually consistent. The user was confused, but the world didn't end. But there are actually cases where it's more important. So a good example is, let's say I have a site like Flickr, and I choose who can see my photos. And I have a list of those people. Let's say I go in, and I remove someone from the list of people who can see my photos, like my girlfriend, and then I post some new pictures that I don't want her to see. But if the system's eventually consistent, she still might, there's a probability greater than 0 that she will see the pictures, which would be a huge problem, potentially. So that's a scenario where you definitely need a higher degree of consistency to get the problem right. So the question is really, it's not that that's bad to have eventual consistency. It's just like, oh, well, yeah, let's just not use it for that particular problem. But it's really just those developers, did we really do the mental exercise to say, yes, it's okay in this particular problem?
So if I have a blog and people are commenting on the blog and people see blog posts out of order or they show up later, or blog comments, maybe that's not too big of a deal.
Right. So on the blog, I think monotonic read consistency would be really nice, right? Because it would be bad if I refreshed the page and comments disappeared. That would be very confusing to me. But if you made a comment and I reloaded the page a second later and didn't see your comment, that's actually fine, right? Because I could have loaded the page 2 seconds earlier. I wouldn't have seen the comment. It's no big deal. Now, however, you would probably also want read your own writes consistency, because if I make a comment on the blog and go back to the page and I don't see my comment, I'm going to be confused. So really, a lot of times, I think on the blog commenting system, eventual consistency works, but what I would really want is read your own writes consistency and monotonic read consistency.
When you say that programmer has to work harder, what you mean is we have to go through more scenarios and say, what if?
You would have had to think about what I just said, whereas, if you put all your comments in Oracle, you didn't actually have to do any thinking. You will get a non-surprising result.
You have also discussed how we can classify these NoSQL solutions in terms of their data storage model. What are the primary classes of storage models in the...
I think this is an important topic that hasn't been discussed enough yet. None of these solutions are relational data model, right? Because we want to make horizontal scaling easy. With relational, it's very hard to scale horizontally. So what all these NoSQL solutions are saying is, let's not do relational, let's make the problem easy, and then we can solve it. And that's what Google did with Bigtable. That's what Amazon did with Dynamo. That's what LinkedIn did with Voldemort. They all said non-relational data store. So the question then, though, we know it's not relational as a data model, but then what is the data model? And I don't think this has gotten enough attention yet. So there's several choices. One is just a pure key value store, and this is what Amazon Dynamo was. So the model there is primary key to value, where the value is just an opaque blob, if you will, of data that we can't reach into. So memcached is a key value store, right? It's not a persistent one, but it's a key value store. So that's a key value data model. So that's really where things started, because that's the simplest thing you could do. So that's one data model. And the really nice thing there is it's so simple that then it becomes very easy to scale, very easy to make it fast, right? Memcached is faster than basically anything. So, but the limit there is that it doesn't do very much, right? I can only do a key value data model. That's a very specific thing. Other choices. So the big table data model is another choice, or variations on the big table data model, basically where you have these sort of multi-dimensional tabular tables things, which have some column flexibility, kind of columnar characteristics to them. So that's one data model. Another data model is what you might call document-oriented databases. So this, by document, we don't mean text document. Think more like XML document. So a document with some structure. And in fact, the way things are going, everyone is standardizing on JSON, JavaScript object notation, for these documents. So we're really storing object-like data in the database in the document-oriented solutions, and specifically JSON format data.
You know that there have been XML databases around for a very long time. XML is another type of document, yet I would make a guess that these JSON databases have already gained more deployments than XML databases and been much more successful. Would you agree with that?
I do.
And why is that?
Well, I think it's a question of timing and what the value proposition was. So when the XML databases came out, I think part of the proposition was easy way to store semi-structured data, an easy way to store XML, and if you're doing a lot of web services in XML, this will be a good thing for you. But I think in practice, what people found is, I get that in my program's talking to the relational database anyway, I'll just keep using that. So that they weren't giving you the horizontal scalability generally, which was really the big driver. That's, because relational is so mature, everyone knows it, everyone's been trained on it. So to move beyond that is a pretty big hurdle, right? But so I need a big value proposition for that. And getting horizontal scalability is a big enough one that people will make the leap. So I think there they just didn't have it. Also, XML is tedious. It's not easy to read. JSON is easy to read for a programmer. It looks just like code, except it's just the data part. We have a standard for it, of course, just like XML. We have an RFC for JSON. Every web developer knows it because you have to know it to build web apps. So it's a very convenient language-independent format for object-like data.
Did you say that JSON document-oriented databases suffer at all from the lack of anything like a DTD or an XML schema to ensure the validity of the entries?
That's a great question. It's possible, of course, in these JSON databases to add some sort of a schema check before you change the data. So you could make them strictly schema'd if you wanted to. In the early days of Mongo, I assumed that we would do that at some point. The interesting thing is that people aren't asking me for that. So I thought we would have done it by now, but we haven't, because empirically in practice, they're not having problems with noisy data, right? So the programmer, it's very common in a collection, which is in MongoDB, you have collections of JSON documents, to have a highly homogeneous set of fields for all the JSON objects in one collection, although there's no requirement for that. What's nice is then you want to add a new field, you can add it to one object and none of the others. You don't have to run alter table, which is impossible once you get to a certain scale anyway. So it's very nice, but the data actually, it tends to just stay clean by itself. And a good analogy perhaps is with dynamically typed programming languages, right? So in a dynamically typed programming language, a lot of errors are caught at runtime when the types don't match, right? And so, my first reaction to that when I first heard of that, 20-some years ago was, wow, that sounds really scary. But it turns out there's a place for that, and it makes development easier. There's also a place for statically typed. MongoDB is written in C++. I like that it's statically typed there. But I also can see why someone would want to use Ruby or Lisp, which are dynamically typed. So here, I think there's a little bit of an analogy there to having kind of more dynamic typing in the database has some benefits. A good example is, let's say you want to store object-type data in the database and you have an inheritance hierarchy for your objects, right? So I have a base class and some subclasses. In a JSON database, if I don't have a tight schema, it's very easy for me to put all those objects, which are everything that descends from the base class, in one collection, because the fact that subclass B had an extra field in it is no problem. It just sits there and everybody's happy. So it actually makes certain data mapping problems quite easy.
You gave a talk this morning about schema design in MongoDB. Talked about the choice between linking or embedding. Tell us a bit about that.
Right. So links are really your kind of like a traditional database foreign key between record A points to record B somewhere else in the database, or in an object database you have links or references between objects. Right. So in an object database there's a lot of linking in your old style object database system, where you just have a big graph of links between objects that you persist. The approach with these JSON databases is radically different, which is that basically you can link, but if you want to link, you got to do it yourself client side by doing an extra request back to the server. So if I need to do some task and I need to traverse one or two links and I'm on the LAN with the database server and it takes me a millisecond round trip to talk to the database, okay, that's a couple milliseconds, that's fine. But if I need to traverse 1,000 links, things are going to get slow, so I wouldn't want to do that. So a little bit is okay and helps me solve problems, but a lot would be bad. So what we do instead of linking is we do embedding. So we build relatively rich documents in JSON with a fair degree of nesting of objects within objects and arrays of objects within objects.
So you've explained already why you can't do a join and have horizontal scalability very easily. To what extent would you say that all the joining that people are doing in relational databases is driven by the fact that they've normalized their data, and that might not be even the most natural way to organize their data?
Part of it is that, and then part of it is another reason, which is just its valid fundamental entity relationship connections between entities. But yes, when you have an order object and an order line item table and you're joining those, you're putting back together what conceptually was one thing, right, that we had disassembled in the database. So we'd taken it apart to a radical extent just to make it fit in with relational model efficiently. So that is an example of something that was that you would join that's sort of artificial. But when you say give me the total amount of dollars this customer has ever spent, and I need to join against the orders table to get that, that makes a lot of sense.
One of your speakers at your conference here this morning said, I don't want to have an elephant sit on my data before I put it into my database.
Yeah, and that's funny. Definitely a lot of that quote-unquote impedance mismatch between object and relational goes away when you use a JSON data store. Now, the interesting thing is that you still do schema design, and there's still a discipline around that. We still define collections in Mongo, we still define indexes, and we still choose what are the fields going to be in these objects. So there's still a discipline around that and how we structure the data, which is relevant. So it's actually quite different from the object databases, where you kind of said, my program defines the structure of the data. Now persist it, right? Because we think here it's actually important to say, I want to put the data in the database in the format that is intuitive to a reader of the database who doesn't know the program code.
Are many different programming languages or popular web framework offering anything like a mapping layer, as are so common with relational databases, to move the data in and out?
Yeah, so there's a lot of frameworks, such as Mongo Mapper for Ruby, which do mapping from, an active record-like thing, for example, which Mongo Mapper is, down to JSON-type serialization into Mongo. So that still exists. However, that mapping layer gets an order of magnitude thinner. So we're still mapping, and there's still some, model frameworks and that kind of stuff. But the complexity of those mapping layers is radically reduced because the things we're mapping between are already pretty darn close.
Your colleague, Richard Kreuter, has a presentation where he says you can organize these NoSQL data stores along yet another axis, which is how they distribute data across a grid or cluster. What are the main representative models in that axis?
Yes, that is true. So there's some different ways to scale out in these systems. One method that was popularized by Amazon, which they originally built in their internal Dynamo product, was used consistent hashing, where you basically put things out on a hash ring, and then that determines what servers they live on and what servers they live on if servers fail. So that's one model of distribution. Is really the consistent hashing family of solutions. The other model is auto sharding, and that was popularized by Google with Bigtable. So in this model, we basically take a bunch of data that we want to partition, and we define key ranges, which are like chunks of data that's, say, maybe 100 megabytes in size. And we keep metadata on those chunks, and we just remember, oh, yeah, all the data in this key range is on shard 29. And then the system does that. And there are pros and cons of the two approaches.
So what would be a couple of key points in favor of the one or the other?
So the consistent hashing is, I think it's elegant and simple. So it is one of the strengths. It's very clear how to add new nodes to the system and how to take them away. So it's very clean in that sense. The auto sharding, I think it's perhaps a little more complex to implement, but the main thing we get there is we get order preserving partitioning, right? So keys that are close to each other will tend to be on the same machine. So if you're doing a range query, that can be important, and that would be difficult to do with a consistent hashing system.
So looking at these systems, this is something I'm trying to wrap my head around and haven't really figured out. I see that you can have something like Voldemort, which is a key value store. It's an A-class system, and it uses the Amazon model of data distribution. And then you have MongoDB, which is document-based, and it's using the auto-sharding model, and it's a C-class system. Can I just pick one from column A, one from column B, one from column C, and get all the properties I want? Or do these three axes somehow constrain each other?
To a large degree, you can pick and choose. So you could say, I want this, this, and this, and now I'm going to go write the system.
The system I'm aware of that's most comparable to MongoDB is CouchDB, at least in the terms of the storage model. How would you compare Mongo and CouchDB?
Yeah, so they're in some ways they're similar. So they're both JSON databases, which I think is a good thing. They're both pretty rich in functionality and features. So they're both towards the high functionality end of the spectrum in the space. The way you talk to and use the systems is quite different. So Couch uses a REST interface to talk to the database, whereas in Mongo we use a native proprietary wire protocol to talk to the database, just like a traditional database. So we actually have a client for every programming language that you can talk to Mongo that uses this proprietary wire protocol. And the reason we did that was for efficiency. So we wanted to build something that was kind of very exact to what we needed to do over the protocol rather than use REST. So it was purely for a performance reason, because otherwise REST would be nice because it's just a nice standard format. So that's a difference. In addition, the way queries work is quite different between the two systems. In Couch, to define a query, you basically create a view which is defined by a set of map and reduce functions, and then it materializes that view effectively. So that is extremely elegant and nice, but it does mean you have to pre-declare these views. In Mongo, we actually do more traditional ad hoc queries. So you give the database a query in the Mongo query language, which is actually JSON, basically. We then run it through a query optimizer, generate a query plan, and run the query. And you can declare indexes just like in a traditional MySQL database. So that's a more traditional approach, but the nice thing there is I get ad hoc queries. Other differences are that Couch is very good at master-master replication with resynchronization after being offline for a long period of time. So if you wanted to write Lotus notes, CouchDB would be really good at that, because that's sort of an online-offline sync-up problem. Mongo is more oriented towards problems where you want a stronger consistency model and you don't want to write code yourself around version reconciliation on merges of master-master replication, things like that. Maybe things where you want global state, like you want to create a unique key index, which would be problematic with master-master replication. So I think it works really well for building, say, web apps, for example, is a sweet spot for it. Couch is written in Erlang, Mongo's written in C++. That's another difference.
Clearly, MongoDB has a much richer set of operations it can do on the server than a key value store.
Yes.
I must be paying something in order to get that, because why wouldn't you want to have all that query capability if you could have it for free?
That's a great question. So our opinion is that it's not going to cost you much, right? So both these big table data model systems and the document-oriented JSON systems, obviously they can represent key value style data. That's a subset of the problems they can represent. So then the question is just, well, are they a lot slower? Am I losing something like that? And I don't think you're losing that much. I think it's a very small hit you're taking on performance. You know, our philosophy is we think as you add features to the database, at some point it gets slower and less scalable. But we think there's a knee in that curve. We think you can add quite a bit of functionality, but when you hit a certain point, if you go any further, you're going to get 10x slower. So we're trying to push as far over towards that knee as we can and no further. So, you know, we want to kind of get to 75, 80% of the functionality of a traditional database, yet have these very interesting new properties in terms of speed, scale, and ease of development. And so we're going to leave out a couple things, but we're not going to leave out 80% of the stuff, which is kind of, if you go pure key value, what you're doing.
How's the MongoDB open source project organized with Tengen as the sponsor?
Yeah, so it's open source. You know, it's on GitHub. At Tengen, we actually started the project originally, but now there are outside contributors and a very active community. There are other companies who are building businesses around MongoDB right now, such as MongoHQ, which is another company that's doing cloud-based hosting in Mongo, which is just using the open source project. You know, it's open source. We love open source, and we want lots of people participating in the community and doing commits and other good things.
What are some areas where the community is especially active in contributing add-ons?
So a few areas, I think there's been a lot of drivers written by the community. There's also been data frameworks that sit above the drivers written by the community, like the Mongo mapper we discussed earlier was written by the community. There have been administrative UIs written by the community. And then the community works on the core database too. And in addition, the documentation, a lot of people make contributions to the docs, translate the docs into other languages. So there's, and just also evangelism, training, all these things too.
What can people do if they'd like to learn more or maybe get involved?
They can email info@tengen.com if they want to get involved, and we'll help them. They could also jump on the MongoDB IRC channel and chat with people in real time and get involved, and we'd love that.
What are some interesting features that people should expect in upcoming releases of the server?
The 1.4 release, so the even release numbers are the stable releases. So those are the ones you really care about. The 1.4 release, which is out now, one of the big additions there was geospatial indexing, which is nice if you're doing mobile apps. You really need that. The 1.6 release, which will be out this summer, is all about scaling. So production sharding and a new release of replication will be out in the 1.6 release, which will really make true production quality large Mongo clusters possible. So that's what all the work today is about. Then in the fall, there will be work on some other things, including single server durability with a new storage engine, work on MapReduce, increased performance, work on full text search and things like that. And not sure the exact dates on all of those, but that's what's in the roadmap going out further.
People are interested in following you. Do you blog?
Yes,
Twitter?
So if you go to the Tengen site and the About page, you'll see links to my blog and Twitter. My Twitter is DMERR, DMER on Twitter.
How many people are using MongoDB?
The uptake recently has been fantastic. So in March, there were 37,000 downloads of the database, and that does not count drivers or docs or anything like that. So that's a pretty clean number, which we think is great for where this market is at this point. And that's up, 6 months ago, that number was 10 times smaller. So we're really seeing very nice pickup and usage of the product. People like Foursquare are using the product now, and SourceForge, GitHub, New York Times. So it's really exciting, and I think the usage is huge.
Do you have any kind of semi-scientific data about market share of NoSQL in the data store market?
Yeah, so it's still small, but there's a clear trend here. It's definitely happening. It's going to happen. We're at a conference here today with 200 people that's sold out here in San Francisco that's only about MongoDB, not much. So, if you project out for the whole NoSQL space, you're starting to get a lot of activity. I think, in the web space, I think by the end of this year, it'll be more people will, if they're starting to build a new web app, will use a NoSQL solution than use a traditional relational solution. Now that's for a web app, right? So that's not in total, right? Because that's the early adopter use case for NoSQL. So we're getting to the point where it's going to be quite significant. But of course, you've got this big installed base of relational, right? So even if we get all of these NoSQL solutions to very high, number of downloads per month, it still takes, say 30 months before that starts to add up into a lot of apps being out there and things being written on them.
Dwight Merriman, thank you very much for speaking to Software Engineering Radio.
Thank you.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the Podsive Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.